Hi, everyone. Welcome back from Reading Week to MATA02, the magic of numbers. Hopefully you guys all had a very studious and productive and hopefully restful reading week. Any questions before we get started? It's been a week and a half. Okay, so a couple quick announcements. As you should probably know, there is a midterm on Friday. So make sure you're there, because if you're not, you're going to get a 0, and that's going to be quite bad for your grade. Another announcement is the results of the syllabus vote are in. So the quiz 3 will indeed be take home. It will not be right after the midterm. Instead, I've decided to make this sort of more writing-based exercise that will be related to some topic that you're interested in. And so if you wanted to, it could lead naturally into the bonus project, if that's something you're interested in. But I'll have more details on that, well, next week, since I assume you all are probably preoccupied this week on the midterm. There is a homework assignment due, as I mentioned, but if you've looked at the practice midterm and the homework, you will hopefully find that the homework is useful for studying for the practice midterm. I will be posting solutions to the practice midterm, hopefully tonight or early tomorrow. We'll see. I need to write up those solutions though. And so if I haven't done that by tomorrow at noon, post me on Piazza, because that means I just forgot to upload it. Okay. So having said that, we're going to, oh yes, one final note, which is that I mentioned this in the announcement email, but just in case you didn't see it, the class is now officially entirely in person. I am continuing to record and live stream, but that will be a second class citizen. So there will be some activities, such as on Wednesday, where I will expect some amount of interactivity that won't really be possible to translate over into onto Zoom. So you're just going to have a worse learning experience if you're on Zoom, at least on Wednesday. But for some of the lectures, they will just be me lecturing here, and in those cases, it is largely equivalent, whether you're here in person or on Zoom. Yeah. Okay, so let's go ahead and get started. What are we going to talk about today? We're talking still about modular arithmetic. That's what this sort of module of the class is about. And we're going to try to think about them from a completely different perspective this time. Oh, wait a moment. Let me grab my notes. Wait, did I not put my notes in here? Oh, what? Oh no, there it is. Good. Otherwise I would have to. Okay. So we're going to talk about something that isn't obviously modular arithmetic, but that we'll see how it's related in a moment. So we're going to talk about even and odd numbers, which are hopefully a concept that you guys have known for ages now. So let's start with easy warm-up, since I know it's been a little bit. If you add an even number and an even number together, what do you get? Okay, yeah, so this is indeed a even. So that's even. Okay, well, let's try that again. Let's do another one. What about even plus odd? Okay, yeah, like 1 plus 2, that's equal to 3. That is indeed odd. What about odd plus odd? Oh, let me zero that out, sorry. Yep. Yeah, so if you have the odd number plus the odd number, that's always even. And somehow this is something that you already know. This is something you learned at some point. Why that's true? Well, you might have learned that, you might not have, but certainly that is something you do hopefully do know to be true. So that's equal to even. Okay, but that's just addition. Well, what about multiplication? Is this a classification number that works well for multiplication? What about even times even? Is that even or odd? Okay, so it looks like the popular vote is for even. And what about even times odd? Let me actually zero. Yep. Even times odd? Okay, it looks like the votes are a little bit slower, but yes, that is indeed also even. 2 times 5 is equal to 10, which is, of course, still even. And lastly, what about odd times odd? Is that even or odd? Yep, so that is indeed odd. Now, I've just been going by the majority vote here, of course, and so the majority vote has been correct. But you notice that I put up a bunch of other options: depends, question mark, none of the above. But somehow, for some reason or another, every time you are adding or multiplying numbers together, the only thing that matters in determining whether the final answer is even or odd is whether the initial numbers were even or odd. So somehow you didn't need to know anything else about the numbers. They could have been 5,000,002 or just the number 2. And somehow for addition and multiplication and evenness and oddness, it doesn't really matter which one of those are, so long as they're even or odd. And so we can write this down into an addition and multiplication table in the same way that we've done for like ordinary numbers or for clock arithmetic. Excuse me. So if we have an addition table, so you might have even and odd. So even plus even is, of course, even. Even plus odd is odd. Odd plus even is still odd. Odd plus odd is even. And we can do the same for a multiplication table. This is multiplication, even, odd, even, odd, even, odd. And so, of course, the punchline is whether the result is odd or even depends only on if the original numbers were odd or even. But now, when I write it down like this, then all of a sudden this starts looking like a number system, right? Because remember, even though we're talking about entire classes of numbers, just all even numbers, they're all odd numbers, well, we have this multiplication table and this addition table. And so you could think of this as we're saying all of the even numbers refer to some number and all the odd numbers refer to some number in some weird number system. Maybe something like our clock arithmetic. And indeed, one of the things we'll find later is that this precisely corresponds to something like clock. Well, it's not just something like clock arithmetic, but this is actually clock arithmetic modular 2. We'll come to that in a moment. Okay, so that's evens and odds. And let's, so the question is, can we generalize this to bigger numbers? So of course, even means divisible by 2. That's how we define it. And odd means not divisible by 2. So can we do the same thing with, for example, the number 3? So what do I mean by that? Well, we define this number even, this term even for any number that's divisible by 2. And then we define this other term odd for any number that's not divisible by 2. So let's try to do the same thing with, well, the number 3. So I'm going to make up some new terms, which you might not have heard before. This is from an example from the Gross and Harris book. So I'm going to call 3even divisible by 3. And I'm going to call throd not divisible by 3. And now, of course, you might be like, well, now you're just making up words. And well, yes, I am just making up words. But now the question is, but I mean, mathematicians make up words all the time, right? The question is, are these useful words to make up? And so anyone want to give some ideas about whether these are useful words to make up or if these are just me being crazy? So will this work? Can we generalize 2 to 3 in this way? What kinds of properties do we care about when we're generalizing these things? Okay, so no thoughts quite yet, but let's give a couple examples and let's see if that sparks any creativity. So let's suppose I have a 3even number and a 3even number. So that means I have 2 numbers divisible by 3 and I add them together. Will I end up getting a number that's 3even? Will I get a number that's throd? Will it depend on what those numbers actually are? Or am I going crazy? Sorry. Yeah. Okay, so most of you seem to have figured out that yes, you do get a number that's 3even. But let me write this out a little bit more formally, just so that we get a sense of why this is the case. So a 3even number is a number that's divisible by 3, so it looks something like 3a, right? A throd number looks something like 3a plus 2, plus r, where r is 0 or 1. Right? Because that's how we define these things. Because If it's not divisible, then it has, oh, sorry, not 0 or 1, 1 or 2. It has to have some remainder, right? When you divide by 3. And so if you add together two numbers that are both 3 even, you end up getting another number that's the same. So for example, 3 plus 6 is equal to 9. Or more generally, we also know that 3a plus 3b is equal to 3 times a plus b. And of course, if you take 3 times a plus b, and a and b are both integers, then that means that the final number is also a multiple of 3. Okay, so at first glance, it's like, well, maybe we're onto something, right? So earlier we were saying if you add two even numbers together, you get an even number. But now, okay, well, maybe if you add two 3-even numbers together, you get two 3-even numbers. Let's keep on going. What about a 3-even number plus a third number? So a number that's divisible by 3 plus a number that's not divisible by 3. What do you get? Okay, so it looks like most people think that this is third. Well, is that true? Well, one way to do it is you can try looking at a couple numbers, but of course looking at just a couple numbers doesn't give you the full story. So 3 plus 5 is equal to 8, but of course you can't check every single one of these numbers for whether or not it's true. But what you can do is you can write this out in more generally. So if your first number is 3a, so a 3-even number, plus a third number, let's say 3b plus r, then this is equal to 3 times a plus b plus r, where r is equal to 1 or 2. And therefore, this is correct. When you add a 3-even number with a third number, you get a third number. Okay, so things are looking good so far, right? Well, the terms we've defined, they seem to have these sorts of addition properties. What about a third number plus a third number? Do you end up getting a 3-even number or a third number when you do this? Okay, so it looks like there's a little bit more separation than what people think, but a lot of people seem to think it really depends. Well, let's try this out. Does anyone want to suggest a third number plus a third number that gives you a 3-even number? Oh, yeah, so, okay, so 7 plus 5 is what I heard, and let's see. So 7 plus 5 is equal to 12. Those are both third, but 12 is 3-even. Some of these don't work. So for example, 3 plus 9 doesn't work because they're both 3-even numbers. So you want to start with two third numbers. What about two third numbers that add together to give a third number? So you have to be careful here. 9 is 3-even because it's divisible by 3. And here we're looking for numbers that begin at two numbers that are third to begin with. So some of the examples that people are giving in the chat are actually not quite right. So what you want is you want a number that's, but 7 plus 5 is correct because 7 is a third number and 5 is a third number. Okay, so we have 5 plus 5 is equal to 10. That's also a good one. So those are two third numbers equal to 10. And 10 is also third because you divide that by 3, you end up getting a remainder of 1. So the answer here is, well, you don't know. It depends. Depends. Let's see. We also have, you have to be a little bit careful when you're doing your addition. So for example, 2 plus 2 is not equal to 6. 7 and 4. 7 and 4 does also work because it gives you 11, which is also third. So something just went wrong here, right? So we originally defined even and odd, and then somehow that was all you needed to know whether the answer was even or not. But when we defined 3-even and third, well, things didn't work out. And well, this is part of the reason why you guys haven't heard the term 3-even and third, is because this idea, so this invention that we just came up with, it doesn't work. And so we're not going to, so in primary school, we're not going to teach you concepts that don't work or aren't useful for anything. But maybe it seems like there still is something here. And so we're going to talk about how you can, like if you're a mathematician going about this, you're like, oh, whoa. So I guess that doesn't work, but can you come up with something that does work instead? But before we go on to that, let's finish off with our multiplication tables and see if this works for multiplication or if it also fails for multiplication. So what about 3-even times 3-even? So if you have two numbers that are both divisible by 3, you multiply them together, are they still divisible by, is the product divisible by 3? Okay, so this one should be pretty easy. The answer is yes. And that's because if you have, say, 3a times 3b, that's equal to 9ab, which is of course divisible by 3. So things like 6 times 3 is equal to 18. What about 3 even times throd? Okay, and of course you guys all, like another easy way of seeing this is just you guys all know about prime factorizations now. And so if one number is divisible by 3, that gives you a factor of 3. And so of course then the final product is divisible by 3. So this is also 3 even. And let's finish off with, well, the last one that's left. What about the throd times the throd number? Does that give you throd? Does that give you 3 even or something else? So this one might be a little bit harder, right? So like, is it obvious that if you take two throd numbers together that you can necessarily always are even or always are odd? Okay, so it looks like yes, this does require some thinking. So any ideas about how you go about showing this? If you have two throd numbers and you multiply them together. So if you have two numbers that are divisible by 3, that are not divisible by 3, and you multiply them together, can you ever get it to be the case that they are divisible by 3? And it looks like we're actually very evenly split on this one. So now this is the job of a mathematician, of course. So now, like, there are several things you could do, right? So one thing you could do is if you're a mathematician, the first thing you might do is you might be like, well, maybe I can just check a bunch of numbers. And if I check a bunch of numbers and I ever get some pair that a pair of throd numbers multiplied together, 3 even number, then clearly that's possible. So let's check a couple small numbers. So let's say, what about 1 times 2? Well, that doesn't work. What about 4 times 5? That's 20. That also doesn't work. Is multiplied by 3. So somehow, let's see. Let's check a couple numbers. Why don't everyone check your favorite pair of throd numbers? So I'm going to zero this out. I'm just going to ask everyone to pick any two throd numbers. They can be however big or small you want, and then vote with whether you end up getting a 3 even or a throd number. And then maybe this will give you some hint about whether or not these numbers are actually 3 even or throd. And when you get it, we'll have you vote on it. And then if we get even a single person who gets a 3 even number, then that would work out. Let's see. So some people are convinced you can't get 3 even, but we do have a couple people who seem to think that they did get 3 even. Does someone want to? I know, like, it's always scary to put something that's different in chat, but maybe you came up with the one exception. So if you put that in to the if that's something you thought you got, if you got a 3 even number, could you put what numbers you got either in chat or just help them out? If not, you can just re-vote and it'll cancel out your old vote, and no one will know that you voted for 3 even. But like, you might have gotten the one exception, and that is important because in mathematics, you only need one exception for something to not be true generally. So let's see. We have 2 votes for 11 times 1 is equal to 11. So that's throd times throd is equal to throd, because 11 is, of course, throd. Okay, so the answer, as many of you have probably guessed, is that it is actually throd. But of course, showing this is a little bit harder. And even though this is true, and even though you can probably convince yourself by just trying a bunch of times, you really need the proof to show that it's always true. And so I am going to write a short proof of this, and hopefully you'll be convinced if you aren't already. So like, when mathematicians are trying to convince ourselves of things, we do a bunch of different things. The first thing we do is we sometimes just try a bunch of things and see if it works out. And if it always works out and we can't come up with an exception, then we might conjecture that it's always true. But then, of course, the hard work is in proving that, well, it is always true. So if this is a Throd number, so that means this is 3a plus r, right? Plus some remainder where r is, let's say r1 is either 1 or 2. Times another Throd number, so that's 3b. Oh, I add an extra line there. Yeah. 3b plus r2, right? So if I have two Throd numbers that I'm multiplying together, we know these are the general forms of a Throd number. Well, if you multiply this out using FOIL, you get 9ab plus 3r1b plus 3r2a plus r1, r2. Okay, everyone follow so far? So this is the product of two Throd numbers. But you notice these are all divisible by 3. Divisible by 3. And these two, this is remember r1 and r2 have to be either 1 or 2. So that means that these can either be, the four cases are r1 is equal to 1, or r1 is equal to 2, and r2 is equal to 1, or r2 is equal to 2. And when you multiply these together, you can only get the values 1, 2, and 4. But of course, 4 is the same as 1 for the purposes of divisibility by 3. And so you can never get a 3 even number when you multiply together two Throd numbers. Everyone follow so far? So that one was significantly harder to really parse than the other examples. But somehow, as a mathematician, one of the things, and so that one was hard, but at the end of the day, it doesn't really matter, right? Because we already know that we don't always get, this is not actually always a good set of terms. And so that's why we don't use them. But now, of course, the question is, can we fix this? Obviously, these terms 3-even and Throd don't work by themselves. But maybe there's another concept that we've been learning that is actually the correct way of going about generalizing even and odd. And that's what we're going to go on to. So it turns out that the concepts that we're talking about right now are another way of thinking about clock arithmetic. So let's start by just relating evens and odds to mod2 arithmetic. So what do we mean by that? Well, remember when we had mod2 arithmetic, we had a clock. We had, oh, I keep on poking at, come on, I click somewhere else. Oh, there, okay. So we have a clock with just two numbers, say 0 and 1. And as you walk along, those are the two numbers in your mod2 arithmetic, right? So you have two options, 0 and 1. But remember, we also had more labels. So if you're walking along on a circle that only has 2 points, and you walk 2 steps forward, you end up back where you started, right? So we also could label this 2. And if you walk another step, this also gives, you can also label that 3. And you can also label that 4, and you can label this 5, label this 6, label this 7, and so on. Or going the other direction, you can also label like -2, -1, and so on. So somehow, what we notice is that the evens, those are all labels for 0, right? In our clock arithmetic, all of the even numbers are labels for 0. And in our clock arithmetic, all the odd numbers are all labels for 1. So remember, when we're talking about clock arithmetic, you only had, well, in the case of mod2 arithmetic, you only had 2 numbers, or in mod3 arithmetic, you only have 3 numbers, and so on. Here, we have all the numbers, all infinite numbers, but we can also think about which of those infinite numbers are labels for the same numbers in the clock arithmetic. And all the even numbers, if you take an even number of steps, starting from the top, you end up back where you started, if you're in mod2 arithmetic. And if you take an odd number of steps on the top, you always end up at 1. Okay, so hopefully you're convinced now that evens and odds are labels for mod 2 arithmetic. So now the question is, can we generalize this to mod 3 arithmetic? Well, let's take a look to see what happens. So well, we have 0, 1, and 2. Say, let me label this here, 0, 1, and 2. So of course, you only have these 3 numbers as in mod 3 arithmetic. But now the question is, what are the labels for 0? So 0 has 0, and then 1, 2, 3, you come back. Another 3 steps, you come back. Another 3 steps, you come back. Another 3 steps, you come back, and so on. So what do all the labels for 0 look like? All labels for, yeah, go on. Yes, exactly. So all the labels for 0 are the 3-bit numbers. So let's write that down. So all those are the 3-bit numbers. These are all labels for 0. What about labels for, but now it's slightly more complicated for the other ones, right? Because for 1, you have 1, 4, 7, 10, and so on. And for 2, you have 2, 5, 8, 11, and so on. And somehow, this explains why Throd was not a good concept. Because the concept of Throd covered 2 different labels. And so I'm going to say, call these numbers 1 Throd and 2 Throd. So this is all labels for 1. And this is all labels for 2. And this explains why it didn't work out, is because although 3-even is a good concept, Throd is not a good concept because it covers too many different things. And if you think about it, as you go on to higher modular arithmetics, if you have like mod 5, 5-even might be divisibility by 5 could be a meaningful concept, but non-divisibility by 5 somehow isn't as important because that covers multiple different remainders. And it turns out, though, that this concept of looking at which labels they are, we already know that to be a good number concept because we already worked out that that works for clock arithmetic. And so somehow what we're saying is that we have the strange world of clock arithmetic where if you walk for a while, you end up back where you started. And now we have this ordinary world of ordinary numbers, but we're looking at the visibility of numbers, and somehow the visibility of numbers matches up with this weird world of clock arithmetic. And I know that when I started this class, I talked about how mathematics is all about like faster ways and better ways of counting. That's only partially true. So that's one of the things mathematicians do. But another thing mathematicians do is to try to figure out that 2 things that look different are actually the same. And that's what we're doing today. We're showing that somehow evens and odds are the same as mod 2 arithmetic, even though one is an infinite set of numbers, or sorry, 2 different infinite sets of numbers, the evens and odds, and the other is just the 2 numbers on clock arithmetic. And what we're showing now is that this is generalized. This idea is the right generalization for divisibility by numbers. And we give these things fancy names because mathematicians like making up words. Some words are more useful than others, like 3-even and Throd are less useful than even and odd. But the names we're going to come up with are congruents. So we're going to use this triple equal sign. So 2 numbers are congruent, mod n, if they're both labels for the same number mod n. So for example, 1 is congruent to 4 mod 3, right? Because walking 1 step and walking 4 steps are the same. And so one way to think about that is that 1 and 4 are labels for the same number. But another way of thinking about them is that somehow they fall into the same class of 1 Throd numbers. Or 2 and 8 are congruent, mod 3. Or minus 5 is congruent to 0, mod 5. Okay? So the basic idea here is, well, we can define these numbers. So we can define 3-even as divisible by 3, which is how we originally defined it. But we can also say that this is the same as congruent to 0, mod 3. Right? So those are the same concept. And we can also write this as just 3a, because we know it's a multiple of 3. And we can define one thread to be remainder of one. Oh, sorry, let me write this in another direction. So we have list as congruent to 1 mod 3. But that means, what does that mean? That means when you step around the circle however many times, you end up at 1. Which of course means that when you step around it a multiple of 3 times and then another step. And so this is the same as saying there's a remainder of 1 when divided by 3. Okay, and we know this because that's how we defined our clock arithmetic. So you walk around some number of times and then you take the remainder when you divide by 3. And so once we know that, then you can rewrite one thread in a slightly different way as 3a plus 1. And similarly, 2 thread, whatever you call this, is congruent to 2 mod 3. And you can also write this as 3a plus 2. And now that we've done this, we've expanded our classifications, right? So it's not just 2 classes, even and odd. We now have 3-bin, 1 thread, and 2 thread. But now, can we do multiplication with these classes? So somehow we're no longer talking about single numbers, we're talking about entire congruence classes of numbers. So let's go back and talk about. So let's start with one we already know. What is 3-bin plus 3-bin? Yeah, so this is still 3-bin. We already showed that earlier, so we don't really need to show it again. And it's still true because we didn't change our definition of the 3-bin class. So that's 3-bin. What about 3-bin plus 1 thread? Oh, zoom out. Wait, zoom out there. Okay, yeah, so the answer here is indeed that this is equal to 1 thread. And why is that? That's because if you have 3a plus, let's say, 3b plus 1, because of course that's a 1 thread number and that's a 3-bin number, you end up getting 3a plus b plus 1. What about 3-bin plus 2 thread? Okay, yeah, so this is just something that's 2 thread. With the same sort of logic. What about 1 thread plus 1 thread? So of course, since we have more numbers now, we have to check all the different cases. Yes, so this is indeed 2 thread. Because you have something like 3a plus 1 plus 3b plus 1, which is equal to 3a plus b plus 2. And what about, come on, erase. What about 1 thread plus 2 thread? Yeah, so this is indeed 3-bin because, well, 1 plus 2 is equal to 3, and 3 is a 3-bin number. And this is the reason why our original classification of just thread didn't work, because it depended on what kind of thread number you're doing to get even a 3-bin or a thread. So this is indeed 3-bin. And let's finish off with the last one for addition, which is 2 thread plus 2 thread. Okay, yeah, so you guys have the hang of it now. So this is just 1 thread. And we can write this all out in addition and multiplication tables. So here I'm just going to use 0, 1, and 2. So of course here 0 is 3-bin. And this is 1 thread. And this is 2 thread. And I'm not going to walk through it by hand, but you can use the same kind of logic that we were discussing to find the multiplication table for these numbers. And one thing you might notice if you stare at these for a moment is this is actually exactly the same as mod 3 arithmetic. So this is exactly the same as mod 3 arithmetic. And so we really are thinking about two different ways of thinking about the same thing. Mod 3 arithmetic, you can think of it as these flock numbers, or you can think of it as the entire classes of numbers separated into classes by what their remainder is when you divide it by 3. But now what's, sorry, dry throat today. Okay. And it turns out this is true in general. So 3 isn't special. We use it because it's small and it's easy for us to reason with. But this turns out to be true for congruence classes mod n, for any n of a summer product. It's determined entirely by just the congruence classes mod n of the numbers being added or multiplied. So let me give a quick example, and then I will actually prove it. So as a quick example, note that if A is congruent to 2 mod 5, and B is congruent to 4 mod 5, then we know that A plus B is congruent to 1 mod 5. So, for example, if I had 12 plus 204, note that one is congruent to 2 mod 5 and the other is congruent to 4 mod 5. This is the same as saying 216, which is the same as 1 mod 5. And this is true for any two numbers. If you know their congruence class is mod 5, you don't actually need to work. You can work with any of the member of a congruence family. But let's prove this because I want to show you guys some more proofs. At some point, I will ask you on a quiz to tell me where I go wrong in the proof. And so it's important that you pay attention to like how I'm proving these things, just the chain of logic, how to think like a mathematician. But not yet. Well, this won't be on your midterm. I mean, the other modular stuff will, but not proofs. You should know from looking at the practice midterm. So let's say that we let A be congruent to K mod n, and B be congruent to L mod n. Okay? So if you know their congruence class, so when I say it's congruent to K mod n, that's another way of saying that when you divide A by n, your remainder is K. When you divide B by n, your remainder is L. So we can rewrite this as A is equal to, and note that when I use equal here, I mean as ordinary numbers. A is equal to K plus xn for some x, and B is equal to L plus yn for some x and y integers. So what does that mean? That means that A plus B is equal to, we just add these together. That's K plus L plus x plus y times n. And so this is congruent to K plus L mod n. So you can always just use another member of the congruence class. And the same for multiplication. A times B, this is a little bit more complicated. This is K plus xn times B, L plus yn. L plus yn. Well, you have to multiply this all out. This is equal to KL plus xnl plus ynk plus xyn squared. But notice that all of this is divisible by n. And so this is congruent to KL mod n. And this allows us to prove the statement we made last time about multiplication. When you're doing multiplication, you don't have to, you can either do multiplication first and then do division, or you can do division first and then do multiplication when you're working in the modular arithmetic. And with that, I think, let's try it out. I think I might run out of time, but that's all right. Okay, so suppose that 68 is equal to 2 mod 6. Hopefully you guys agree with me that that's equal to 2 mod 6. You should check. And suppose that 293 is congruent to 5 mod 6. Is that right? Yes, that's right. Okay. So what is 68 plus 293 mod 6? And let me zero that out. Okay, yeah. So one way you could do it is you could add them together. So you end up with 361 or something like that. So that's one thing you could do, and that would work. But it's easier if you do just say, this is congruent to 2 plus 5 mod 6, which is of course congruent to 7 mod 6, which is congruent to 1 mod 6. And so it's a lot faster when you do it might be easier if you do the division first. This is especially the case when you're dealing with multiplication, because that often gives you much bigger numbers. So what is 68 times 293 mod 6? Okay, so yeah, so it's what we get. That's congruent to 2 times 5, which is congruent to 10, which is congruent to 4 mod 6. And so you see, this is a much faster way of doing multiplication in modular arithmetic, because you don't have to worry as much about really, really big numbers. And you'll notice that on some of the problems in modular arithmetic I give you, if you were to try to do it naively, the numbers you get are way too big. I've chosen those numbers specifically because they're way too big for you to have when you're calculating. Because I want you to actually understand modular arithmetic and not just multiply everything through and then divide. Okay, so having said that, this is really a different way of thinking about modular arithmetic. So one way of thinking about it is adding or multiplying the other points on the clock. So that's the original way we thought about it, right? So you have some clock, and so you have 0, 1, 2, 3, 4, and you look at how many steps you walk along, and you just have these 5 labels. But another way of looking at it is adding or multiplying together entire classes of congruent integers. So anything like -10, -5, 0, 5, 10, 15, those are all congruent under mod 5. And so you can think of those as labels, or you can think of them as just all the numbers that are divisible by 5. 5 if we were to use the silly naming scheme we were using earlier. But because mathematicians have to do this for all numbers, we usually just call it 0 mod 5. And then you also have 1 mod 5. So that gets you like -4, 1, 6, and so on. Is it wrong if we add 68 and 293? No, it is not wrong. But there will be times when that won't be possible because your numbers are too big. You should check, actually. So the whole claim is that it doesn't matter which one you do. And so sometimes you want to do the easier one. And yes, I know if you have a calculator, it might seem, well, the easier one is just to type all the numbers in and throw it in the calculator. But that won't always be possible. And I will make sure it's not always possible because I want you to actually understand what's going on. Let's see, for 2 here, you have things like -3, 2, 7, and so on. For -3, you could have things like -70, 97. Of course, 3 also works, 8, and so on. And for 4 here, things like -1, 4, 9, and so on. And but yeah, that's a very good question. And it gets to the point, which is sometimes certain orders of operation are easier. For example, let's suppose I gave you this particular problem. So I ask you to multiply these numbers. I'm not even going to try to read them because I'm just going to mess it up. Divided by 437. So now the question is, if you're going to do this, what is the correct way of doing it? Should you multiply first? Should you divide the bigger number first? Should you divide the other number first? Does it not matter? Or none of the above? Okay. So it looks like a lot of people have said that you should multiply first. Let me ask you a slightly different question, which is, what would you do if you didn't have a calculator? I'm going to let you re-vote again on this. Suppose you didn't have a calculator, or maybe your calculator only goes up to 100 because you have a really silly kiddie calculator. Yeah, so if you try this out, what you'll find is that multiplying these numbers out can be really, really big. And so sometimes you might want to change the ordering. So if your numbers are small, then maybe it makes sense to multiply first. If your numbers are really, really big, then sometimes you want to divide first. I mean, the answer mathematically is that, of course, it doesn't matter which order you do it, because multiplication and division are on the same scale in terms of ordering. So at the end of the day, you will get the same answer, assuming you do everything exactly. But it does make a difference in practice. So sometimes you want to work with smaller numbers that can fit on your calculator or in your head or on your sheet of paper. And for that, it sometimes does matter which order you do things in. And that's basically the point I'm making with modular arithmetic, which is you can always replace numbers with any number from their congruence class. And sometimes this can make your computation a lot easier. So for example, if you had 224 times 376 mod 17. So one way of doing this is you can be like, okay, well, I'm just going to multiply together on my calculator. This gives you 84,224 mod 17. And then I'm going to do the division and get the remainder. And that's congruent to 6 mod 17. But another way of doing it is to first do the divisions. And you'll notice that this is actually equal to 3 times 2 mod 17. And this is congruent to 6 mod 17. And so you get the same answer either way. But one way keeps your numbers smaller. And let's see. And I think I am, okay, I'm not going to have time for everything, but let's finish out by just talking a little bit about some of these. Yes, I'm dividing by 17 to get 3 and 2. That's exactly what I'm doing. And hopefully I did that right. So there are a couple common tricks that you use, and these tricks are ways of basically making your computation easier. And sometimes the computation will be so hard, even your calculator can't do it. So when working with really big numbers, sometimes it helps to replace really big labels with some label that's smaller, right? So if I'm in mod 1000 arithmetic, replacing 1002 with 2 makes life easier. Alternately, sometimes, let's give another example. Let's say I have 4 to the 6 mod 17. Well, this number is small enough that you can't actually do it by hand. So this is equal to 4,096 mod 17. And if you use a calculator, this gives you 16 mod 17. Okay, well, that was a little bit painful because you had to multiply it all out and then you had to divide. What happens if you rewrite this in a slightly different way? So I'm going to rewrite this as 4 cubed times 4 cubed mod 17. So what's that going to be? That's going to be 64 times 64 mod 17. Well, what's 64 times 64 mod 17? Well, if I replace these numbers, you'll notice that 64 is congruent to 13. So this is 13 times 13 mod 17. Okay? And then this is equal to 169 mod 17, which is congruent to 16 mod 17. Okay, so that's a little bit easier, but not super duper easier. But sometimes you can even make it even easier by using negative numbers. So for example, 4 to the 6 mod 17. Well, we can also rewrite this a different way, which is this is 4 squared times 4 squared times 4 squared mod 17, right? So another way of writing this is 4 squared cubed, which is of course congruent to 16 cubed. But now, what's something special about 16 mod 17? What's another way of writing it that might be easier than 16? Yes, -1. Yep. So this is congruent to -1 cubed. But now -1 cubed is really easy, right? So that's congruent to just -1 mod 17. But of course, -1 mod 17 is exactly, well, still 16 mod 17. And let me finish off with one more example. I won't get to everything in today's lecture, but that's all right. Which is, let's say 439 times 632 mod 633. Well, here, one way of doing this is to write this all out. That's 277,448 mod 633, which is painful, but that's congruent to 194 mod 633. Alternately, this is also congruent to 439 times -1, right? Because 632 is -1 mod 633. This is congruent to minus 439 mod 633. And what's another label for that? Well, you can just add 633. That's congruent to 439 plus 633 mod 633, which is congruent to 194 mod 633. Okay, and with that, I think I have my other slides are just a couple more examples that we're going to work through. We'll work through these on Wednesday because you should practice your modular arithmetic for your midterm. And with that, quick announcement, which is that there will be an interactive activity on Wednesday. So come prepared to talk to each other as well. So I'll just be aware of that. And with that, thank you all very much. My office hours are earlier today. So they're at 11 o'clock, not at 12. So I hope that I send out an email with the room number. So with that, see you on Wednesday. Bye, everyone.